Hi everyone, I'm Carl and my teammate is Jisoo, and our group is called Bio-Inspired Printable Masks. So as you probably know by now, these are surgical masks, and they're used everywhere. It's been reported that over half of mask wearers use them on a weekly basis, and globally, 129 billion of them are thrown away each month. These masks are not great, and we'll show you why. So take a look at this video, which visualizes breathing through a surgical mask. So we see that breathing causes a lot of air to escape out the sides of the mask instead of going out through the center. This is dangerous since it could allow contagious particles to spread farther in the air to potentially come into contact with others. So there are many reasons why surgical masks are not great. In addition to the safety concerns around the poor face fit that we already showed you, there are also considerable environmental concerns, being that they are non-reusable and cause excess waste. It's estimated that from the past year, we'll spend $40 billion on cleaning up the masks and other disposed medical waste from COVID-19. Finally, there are comfort issues with masks since they restrict our breathing and cause glasses wearers like myself to have poor visibility from fog. So in this project, we'll propose a new mask design which will help solve these issues. To address the environmental concerns, our mask will use 6 times less filter material than surgical masks and be largely recyclable. For safety, our mask will have an improved face fit to minimize air gaps. And for comfort, our mask will it'll reduce the chances of fogging glasses and even add a mechanism for breathing relief. So now we'll introduce our new 3D mask design. It consists of the mask base, which touches the face, a cover, holes for the head straps, and on the bottom there's a knob which controls an added breathing relief valve. Upon expanding the components, we can see further details inside the mask, including the internal filter and housing for the smart components, which we'll discuss later on. Here are some other views of the mask as well, showing the front, side, and inside view of the structure. And this is what the mask looks like in real life and on my own face. The colors are a bit different, but the design is still the same. You can also see how 2 straps are attached and wrap around the face for its support, the straps in white. Now we'll go into how the breathing relief knob works. So we've circled the knob on the left, and here's a video to show what's going on when you turn it. So to better understand what's going on, here's a cross-sectional view of the mask. And if we zoom in on the structure itself, we can see that it consists of many channels running radially from its center. Basically, by twisting this breathing relief valve, one can allow more air to pass through, as shown on the left, or even cut air completely off, as shown on the right. And now Jisoo is going to show you how our mask improves upon the issues of environment, safety, and comfort.
Okay, from now on, I will explain how our mask works in terms of environment, safety, and comfort. First, in the environmental aspect, our mask uses a much smaller filter, so it reduces overall waste over time. Compared to the surgical mask, our mask filter region takes up around 6 times smaller. Also, we can reuse the external mask by disinfecting or washing. Additionally, we can print this mask with recyclable plastic. Regarding safety and comfort, we conducted experiments with the human head structure and demonstrated the improvement. Moreover, we made a piston setup with pipes to simulate human breathing. The human head model is attached to the left side of the pipe. On the right, there is a piston and it moves back and forth to make airflow. When the piston moves to the left, it doesn't exhale, and when it moves to the right, it inhales. About the condition, surgical mask filter was used and piston speed was 48 centimeters per second, and it is around 120 liters per minute. Under the setup, we checked that our experimental setup provided a good simulation for actual breathing. To check this, we measure the pressure drop by an Arduino nanosensor during the piston moving. And on the right graph, the green part is a breathing simulation using the piston, and the sky blue part is breathing when car was wearing the same mask directly. And in this graph, pressure sign means the exhale, and the minus pressure indicates inhales. Even though the amplitude is different, both data has the same sign graph. So the piston mimics breathing well. For the following experiment, we set the piston speed as 48 centimeters per second, which is similar to car's rear breathing. And let's talk about the safety aspect first. We confirm that our mask has less air leakage compared to surgical masks. In this experiment, smoke particles were used for visualization. Let's play the video and please pay attention to the square boxes. In the case of a surgical mask, most of the air passed through the openings in the cheeks and nose. With our mask, there was a leaking air from the chin. However, a relatively smaller amount was leaking than surgical masks. Since our is a prototype, we know that there are many leaking regions, but we are trying to make improvements to reduce this further. Next, we found that glasses are much less likely to fog up when using our mask. Kai compared the surgical mask with our mask himself. When he wore a surgical mask, he easily got fogged up like this image. This is because the nose part was too loose and air escaped it through this part. On the other hand, with our mask on his face, the glasses are clean. Therefore, our mask fits more tightly on the face and is comparable as it prevents fogging on the glasses. The fogging of the mask is associated with both safety and comfort aspect. On top of that, we also tested the breathing relief valve in the aspect of comfort. First, we observed that when the breathing relief valve is closed, all the air passes through the front filter. Please look carefully at the square boxes in the video. Yeah. Since the valve is blocked, all air does not pass through this bottom part, so most air moves through the front side. Also, we measure the pressure drop inside the mask too. As well, we tested the 100% open breathing relief valve under the same conditions. When the breathing relief valve is all the way open, a lot of air passes through the bottom part. Therefore, okay, let's see the video. So therefore, different from the closed case, you can see the smoke particles both on the front and bottom part. Let's directly compare the case of 100% with the case of 0% opening. Please focus on the red boxes. Here clearly, we can see that the smoke only flows out the bottom of the mask when the breathing relief valve is open. Plus, we analyzed the pressure drop data and confirmed that the breathing relief valve can reduce the breathing resistance. To do this, we measured the pressure drop when the valve was opened with 0, 50, and 100%. The graph on the left is raw data, and we calculated the amplitude and plot this on the right. This graph shows that the higher the opening rate of breathing relief valve, the lower the pressure drop. In other words, it makes it easy to breathe. From this, we demonstrated that this valve can control the level of breathing. And next, Carl will talk about the future direction of our mask.
Thanks, Jisoo. So our mask is cool and all, but there are many other commercially available masks out there which solve some of these issues already. Therefore, we wanted to explore further possibilities to differentiate our mask from what's already out there. So in addition to addressing the three original issues, we've also been working on a unique digital component we call smart features. So similar to how smart watch reads data from your wrist, our mask will read data from our heads and the air we breathe. What we call smart features are biometric data-related features which may be delivered to your phone by connecting over Bluetooth. In our prototype, we use the Arduino Nano 33 Cents as our microprocessor, which packs a ton of features and functionality into a small form factor. Using this processor allows us to sense tons of different biometric data from breathing and the face. Its sensors include a temperature and humidity sensor, an accelerometer, a proximity gesture sensor, a pressure sensor, a microphone, and even much, much more than this. So now there are numerous possible ways to use all this biometric data. So in the following slides, we proposed just a few different scenarios. Scenario one is using the pressure sensor to monitor breathing and coughing to help diagnose sickness. In the video you're about to see, pay attention to the black computer monitor, which shows real-time pressure data from inside the mask. So as soon as I put the mask on, you can see the pressure oscillating due to the breathing. And right there, you could see a huge spike from when I cough, which could give a clear indication for diagnosing sickness in patients. So scenario two is similar to the first, but now it's using the pressure sensor to monitor breathing during exercise. So I'm about to do some push-ups and pay attention to the frequency and amplitude of the pressure curves on the screen. So using this method, athletes could get more information on the way that they breathe, which could be used to better improve their workouts. Scenario three is using the microphone to make voice calls by speaking inside the mask. Since the microphone and all their sensors are positioned inside of our mask, this could provide a method for making voice calls without being muffled, like when speaking through a cloth mask. Scenario four is using the proximity sensor to recognize how long you've been wearing the mask to notify when to change the filter. So here's some data I took using the proximity sensor, showing distance from the mask versus time. Here, it's pretty clear when I'm wearing the mask, as it reads 0 for the distance, as you see in orange. But when the mask is off, then you see the distance reads a high value, which you see in blue. Using this information, the mask could notify the user when it's time to change to a new filter based on how long the user's been wearing the mask. And finally, scenario five is adding a motor to actuate the breathing relief valve automatically. I'll play the video for you. So this could possibly be used to provide optimal settings for the breathing relief valve based on biometric data such as how hard you're breathing or coughing at that moment. Finally, for potential work in the future, we may continue refining the dimensions to reduce air leakage by changing building materials or tweaking dimensions. We may have user testing of our mask to incorporate feedback, or we may further develop the smart features by brainstorming new biometric methods, creating more robust algorithms for detecting and responding to breathing, or creating an app to interface our mask with a smartphone. So thank you for listening, and we look forward to answering questions.